Hi, I'm your guide in the next few minutes for a voyage through a new chapter of OPC UA, where it explores a strange new IoT world and boldly goes where no industrial protocol has gone before. In today's episode, OPC UA will learn to speak MQTT to spread its data in a more efficient way. But let me first introduce myself. I'm Hannes Radatz and working for the Institute of Applied Microelectronics and Computer Engineering at the University of Rostock, which is the oldest university in the Baltic Sea region. So let's start with the motivation. Why do we need the publish-subscribe communication pattern at all in OPC UA? Well, OPC UA itself is a client-server based protocol, so it uses the request-response communication pattern for the information exchange. However, additionally, it also supports a so-called subscription feature, which is again based on the client-server pattern and enables something like the notification feature we know from smartphone notifications, for example. So what are the pitfalls of these available solutions and why do we need to go for the publish-subscribe pattern? As you can see on the left-hand side, we have here the normal request-response pattern depicted, and if a PLC, for example, wants to request information from another PLC, it requests information and gets a response back with this information. As you can see in the scenario, here we have maybe one important PLC which offers information where other devices are interested in it. So many other PLCs request the same or may also different information from the PLC and get a response back. The problem here is that this request-response pattern is based on session. So every time a session has to be built up in both end devices and needs to be maintained until the request is fulfilled or until all follow-up requests are fulfilled. So may also a long time. So this fills up the RAM in the devices if we have open connections to several devices. If you look now at the subscription feature in the middle figure, here we solve one problem. One problem is here that the device still needs an initial subscription to the data in the PLC is interested in, but then after this, there's no more request necessary to get updated information about this data. So notifications are just sent out if the value in the PLC is changing. So we reduce here the communication effort. Nonetheless, the session management in the RAM is the same. So we still need to maintain for every connected PLC a session. So now look at the right side at the new publish-subscribe pattern. Here we have still the same principle. We have PLCs which are interested in information from one PLC, but this time we do not need to maintain sessions for all these PLCs. We basically just to maintain one session. And this is also not changing if we differentiate between the brokerless approach, which you can see now, or the broker-based approach, which you can see here. There we have a broker in between, and again, we just need to maintain, in this case, the session to the broker, but not to the all other interested devices. So we have far less RAM consumption. So let's dive a bit deeper into the advantages and disadvantages of the publish-subscribe in general. As I've explained before, the advantage is that we now shift the effort for the session management and also the data distribution itself either to the network or to the broker. The disadvantage is that we start to miss the feedback due to this one-way communication. So we also hand over the reliability check of the transmission to the network or to the broker. If you look a bit closer to the different possible solutions, we have the brokerless and the broker-based approach. The brokerless approach is often the multicast approach. So the advantage here is that we do not have a broker device in between, so reduce the latency between the publishing device and the subscribing device. For this approach, we have the following disadvantage. We will use the so-called UADP, which is a combination of UDP and multicast combined with binary data encoding. And this multicast requires specific network switches. In detail, they need IGMP network switches. So if they are not already there, it's maybe a costly upgrade. Looking with this to the broker-based approach, we have here the advantage that we, besides the session storage in the RAM, we can also decouple the devices effectively. For example, there's no need anymore for both devices to be online at the same time. This is especially interesting if we have, for example, a temperature value that is based on energy harvesting. So it has its own schedule when it will boot up, send data to the network and go sleeping again. The disadvantage we may have here is that we have now a two-hop communication because we have the broker in between and therefore higher latency for a single transmission. So why do we decide for MQTT? There's an OPC UA standard amendment, which is now the part 14, and this part 14 takes care about the publish-subscribe feature. So it describes how one could extend the existing OPC UA protocol by a publish-subscribe functionality. In this part 14, they propose UADP, so UDP over multicast with a binary data encoding as a brokerless approach, and they also highlight MQTT and AMQP as possible broker-based approaches. So in the most common OPC UA project, Open62541, there is already new UADP implementation existing. So we ask ourselves, how can we now do a comparison to evaluate this part 14 amendment? We decided to implement broker-based approach to compare then against the brokerless approach. And we decided to start with MQTT. Let's start with the concept. The part 14 amendment of the OPC UA standard is a rather complex and comprehensive document which has a lot of details. So rather than describing it now in the presentation, I would refer to the paper for detailed information. As you can see on the left-hand side, we have here the OPC UA server, and on the right-hand side, the OPC UA client. So except using this communication flow, we replace it by the part 14 pub/sub communication layer and transmit the message, in our case, over MQTT by encoding the data in JSON and then inherently via MQTT broker to the now called subscriber. So let's come to the implementation. Which libraries do we use? We used, as already mentioned before, for OPC UA, the GitHub project Open62541, which is one of the best supported and maintained projects out there. And this is open source. It is written in C and C++, and it also partially supports already publish-subscribe. So why partially? Because UADP, so the UDP multicast variant, so to say the brokerless option, is already supported. However, the MQTT implementation is started, but for example, the subscription was never finalized. On the other hand, we have the MQTT libraries. So here we used two libraries. We used the MQTT C library for the clients, so for the subscription and publishing functionality. And we used the Mosquito library, which is part of the Eclipse community for the broker. So we do not touch the broker, we just used the existing Mosquito broker. Let's have a quick look at the evaluation. The testbed consisted of two devices which were connected via 100 Mbit Ethernet switch. These two devices were synchronized by NTP time synchronization. Furthermore, when we talk about in the next slides about transmission latency, we mean the transmission time, which includes the delay in the software itself, the network stack, and the physical transmission time over the medium. So in the first scenario, we had a look at the transmission latency over different transport profiles. One was a client-server subscription. The second one was a publish-subscribe UADP brokerless version. And the third one is a publish-subscribe MQTT, so a broker-based. On the left-hand side, you can see the points where we took the timestamps for the three different versions. And on the right-hand side, you see the bar diagrams which reflect the latency. As you can see, MQTT ranges in between client-server subscription and UADP. So UADP is the fastest one, and client-server subscription was the slowest one. MQTT was exactly in the middle. why we expected UADP to be faster, we are quite surprised that the client-server subscription was slower because it has not a broker in between. So this will be investigated in future. The next thing we wanted to evaluate was the transmission latency only of the MQTT JSON transport profile, but with different payload sizes. What you can see here is a communication with either 1, 2 or 7 variables in the payload of MQTT. And what we found out is that the processing time of the broker is always the same, that is the orange share of the bars, which is expected because MQTT doesn't care about the payload. Then the blue shares are the time between the publisher to the broker, which are nearly the same independent of the variable count. However, this doesn't hold true for the green share of these bars. As you can see, if we have a higher number of variables, then the transmission time increases unexpected. So this will also be investigated in the future. After we verified the functionality of our implementation, we thought of another extension of that, and we called it the remote publication mechanism. Basically, it is a functionality to remote control the publishing of the publisher. So we want to select as a subscriber which information is published by the publisher. Currently, the subscriber has no control over the published data due to the basic concepts of publish-subscribe communication pattern. So we regain the control via a temporary client-server channel to change a so-called publication list, which is a variable in the address space of the OPC UA publisher. And this publication list contains all data IDs, so node IDs on OPC UA, for the data that is published by the publishing layer. When the subscriber browses to the address space, he can find out the node IDs of all data he's interested in. Then he can alter the publication list and add the IDs for the data he's interested in. The publisher reacts on change of the publication list and updates its publication layer. So finally, the newly selected data from a subscriber is published to the broker. Let's come to the conclusion and outlook. So for the summary, what did we do? We interconnected OPC UA instances via MQTT, and we followed the OPC UA Part 14 standard amendment. We also encoded semantic data from OPC UA with JSON, we transmitted via MQTT. We did some very first preliminary latency evaluations that showed that the MQTT transmission ranges somewhere between the slower client-server subscription and the brokerless publish-subscribe UADP. We further investigated a so-called remote publication mechanism, and when we have a look for the upcoming things, what we will do is we will confirm the results. So as I said, we just had a very first preliminary latency evaluation here. This will be done more in details, looking into the difference between the client-server subscription and MQTT, for example. What else do we want to do? We will have a look at the scalability, so we will measure MQTT performance with multiple subscribers. We will also have a look at the compatibility, so we will have a look how can OPC UA talk to generic MQTT clients, because currently we need on both ends OPC UA and devices. Next point is the comparability. In future we will also have a look in the AMQP layer, so we want to add AMQP to OPC UA. And what we're already doing right now, we write pull requests for the GitHub project Open62541 to add our completed MQTT implementation. Finally, I have to thank you all for listening. Our episode comes to its end, and the one remaining thing is I can tell you live long and prosper. And do you have any questions or remarks for this presentation or the recording paper, then please send me an email to the email you can see here. Thank you.